In this lesson, we'll be exploring the RGB LED. An RGB LED contains three individual LEDs, red, green, and blue, all housed in a semi-transparent casing. By varying the voltage to the red, green, or blue LEDs, we can create a wide range of colors. Let's begin by looking at the schematic and identifying the components of the RGB LED module. First, we have the pins. The VCC pin provides power to the LEDs and will be powering the module with 3.3 volts to ensure compatibility with the Raspberry Pi GPIO output. Then there are three control pins, R for red, G for green, and B for blue. Additionally, we have three 330 ohm resistors. These resistors protect the LEDs by ensuring that the current doesn't exceed safe levels. To understand how this RGB LED module works, we're going to connect it to our GPIO extension board and test each individual LED. Grab your RGB LED module and a 4-pin connector. The first circuit we'll test is the red LED. To turn it on, connect the VCC pin, the brown wire, to the 3.3 volt power source at physical pin 1 on the GPIO extension board. Next, take the R pin, white wire, and plug it into the ground pin. I'll use physical pin 9. At this point, your LED should illuminate red. Next, let's test the green LED. Leave the VCC connected to the 3.3 volt pin. Connect the G pin, the red wire, to the ground pin. I'll again use pin 9. Your LED should now light up green. Now, to light up the blue LED, connect the VCC to 3.3 pin and the B pin, the black wire, to a ground. I'm using pin 9. Let's see what happens when we light up two LEDs simultaneously. Start by connecting the VCC to 3.3 volts at pin 1. Then plug in the R pin, the white wire, into the ground at pin 9. Next, connect the G pin, the red wire, to the ground. I'm going to use pin 25. You should now see a yellowish color, which is a combination of red and green LEDs. Finally, let's light up all three LEDs, red, green, and blue. Keep the VCC connected to the 3.3 volts and connect the B pin, the black wire, to ground. I'll use pin 39. Now your LED should appear white. Depending on the quality of your LED, you may still see traces of the individual colors, since they may not blend perfectly. This LED represents a pixel. Now, let's build on this. We saw the RGB LED is similar to a pixel, although larger, and the blending may not be perfect. To better understand color combinations, you can use an online RGB Colorpicker, which shows how different values of red, green, and blue combine to create millions of colors. When we tested the LED earlier, we applied full power to the red and green LEDs, turning them on fully. This corresponds to a value of 255 for each color channel, meaning 100% on. 0 meant the blue LED was off. This gave us a yellow color. Now, if we wanted a specific color, like a mix of 126 for red and 145 for blue, we would need to control the brightness levels of each LED. This is where Pulse Width Modulation, PWM, comes in. PWM allows us to control the brightness by adjusting the duty cycle, the percentage of time the signal is on. For example, to achieve a red value of 128, which is halfway on, we would use a 50% duty cycle at a frequency of around 100 Hz. This would average out to about 1.65 volts, representing the desired intensity. To program this LED using Pulse Width Modulation, we'll need to connect the RGB pins to GPIO pins capable of Pulse Width Modulation. The VCC brown wire goes to 3.3 volts. The R pin, the white wire, goes to GPIO 17. The G pin, the red wire, goes to GPIO 18. And the B pin, the black wire, will go to GPIO 27. With this setup, you can pulse width modulate each LED to create any color combination by adjusting the duty cycles for red, green, and blue. We will be programming this in the next lesson.